Hello and welcome to this video on finite element analysis, Contact, the application of Contact. My name is Mike Fiedler and I am a designated support specialist with Autodesk, and I'm going to be working through today's presentation with you. We're going to take a look at a small assembly within Autodesk Inventor Nastran, and we'll take a look at the different types of contact available and talk about how to set up the contact. So let's go ahead and start with the model inside of Inventor. So here's our larger assembly inside of Inventor, and I'm just going to start with a smaller portion of it. We're going to take a look at this yoke plus some of the components around it, and the model will be provided, so feel free to open up the geometry. I'm going to go ahead and open up the geometry now, and the model we're going to work with is called yoke assemb quarter. So whereas this geometry is the full model, I have already quartered the geometry down just to make it a little bit simpler and show how this is going to make the analysis faster. So you can see here that the bottom half of the geometry has been cut away as well. If I rotate it this way, the right side that is gone is a mirror image of the left side. So we've cut it in two different directions, and ultimately we'll have to apply our symmetry constraints. Now, as far as the setup is concerned, what we're going to do with this geometry, you can see that we have a plate here where the bolts would go through, and then there's a spacer, and then the yoke itself. So what I'm going to do is fix the surfaces where the bolts would go, and then we'll use contact between that component and the spacer and the yoke. And then at the opposite end of this geometry, on the yoke in the hole here, is where we'll apply the loads to this geometry. So let's go ahead and go into the environments, and then we're going to select Autodesk Inventor Nastran, and we can get started with the setup. So the first thing I'm going to do is just take a look at the material. It has a mild steel associated with it. That'll be okay. We'll accept that. One of the other things that I do want to take a look at is to go into default settings, make sure that my default settings are set up appropriately. These are the default options. I'm going to go ahead and say OK to that. You might want to do a quick check comparison to what your settings are. The one thing that I do think I have off is this save FEA modeling data. What that means is as I exit the model, it will not save the FEA modeling data. So it's just saving me a little bit of space. Plus, as I go through the models, I might want to set them up in a completely different fashion. So for my work here in creating the videos, I'm not saving the FEA modeling data. But in your normal day-to-day work, of course, you're generally wanting to save the outcomes of your analysis, so you might want to have a check mark there. The other thing I'm going to take a look at is under Analysis. When I double click Analysis, I'm going to go over to the options, and we'll stop here for a moment. Since this video is primarily about the contact, you'll see that the default type of contact here is set to bonded. So when we define the contact, presuming that we're going to utilize solver contact, or if we're going to do automatic contact, what that means is the default setting that the program will apply is bonded. So you can certainly change it here if the majority of your model is going to be something else. So if I know that, say, 90% of my geometry is going to be in a separation type of condition, I can set this to separation so that whenever I go through and have the program automatically figure out where my contact pairs are, for instance, it'll set them all to separation contact, and then I can go back after the fact and just change a few of them to bonded. That'll make a little more sense here in a little while when we actually go ahead and apply the contact, but I just wanted you to see that this is where the setting is found under Analysis, and by default it's on bonded, and I'm going to go ahead and leave it at that setting. Let's go ahead and do our loads and constraints. So the sequence I'm going to do would be the constraints, the loads, the mesh, and then we'll do the contact. So the first thing is where the geometry here is going to be fixed. And so I'm going to take these surfaces where the the bolts might touch, and we'll go ahead and fix those surfaces. So we have 1, 2, 3, 4 surfaces right there, and that's going to be my fixed constraint. So let me assign some name to it, since we are going to have several different types of constraints in this analysis. Now the other thing I have to do is add my symmetry constraint. I cut away the lower portion of the model, and you can see the vector perpendicular there is the y direction. So I need y symmetry constraints in those locations. So let me go ahead and rotate the geometry around. So that would be all the surfaces there that are on that symmetry plane. So let me go ahead and select constraints again, and this is going to be what, my y symmetry. So let me assign it that name, and then we'll select the y symmetry, right, ty, rx, and rz, and then I'm going to go ahead and start selecting all the surfaces on that symmetry plane, or that cut plane. There's those. Just pan the model over a little bit. So there are a number of surfaces here for that. Doesn't take too long though. And so it's a little bit of time in the setup when you use the symmetry constraints, because you do need to select those surfaces and define those symmetry boundary conditions. However, we will save time in the actual analysis. So those are all the ones that lie on the xz plane, y vector perpendicular. We've already assigned it a name. I'm going to go ahead and say OK. That will add the constraints there. And then the only other one that we need would be our z symmetry constraint. Bring the model back in the view here. Rotate it around. On this back face here, this is where my z would be the perpendicular direction, so that's where my z symmetry is going to go. So I'm going to go constraints, and again we'll assign the name to that one, z sim, symmetry z, and then I need to select that surface that lies on that symmetry plane. So there's, oops, I have a y symmetry. Let me change that to z symmetry. There we go. tz, rx, ry. We'll say OK. OK, so that does it for my boundary conditions, right? So I have my fixed ones here acting like the bolt, if you will, and then the other ones were only necessary because of the fact that I quartered the model, made a quarter symmetry model. Now, when I decided that I would do this model, as far as loading is concerned, what I want to examine is this end of the geometry is fixed, and maybe there's a 10,000 pound load being applied by, say, a pin or something like that in the yoke. I will give you that it probably touches more than the inside circle here of the hole, but just for simplicity's sake, I'm going to apply it all to the yoke part. So I'm going to go to loads, and I'm just going to grab that surface right there. Okay, so that face on the yoke, that half circle face, since we've already cut it. Now, as far as load is concerned, this is going to be a force, and I just mentioned a minute ago that in the full model it would be 10,000 pounds force. But since we've quartered the geometry, then of course we need to adjust our load accordingly. So this is going to be a 2,500 pound force, and we'll say OK. Alright, then let's go ahead and generate the mesh. Generate mesh. Okay, so the program is going to assign some mesh to it. And you can see that it has a coarser mesh out here along the yoke, and it does put finer elements around some of the smaller features of my geometry. I just want to go overall a little bit finer with the mesh. So to do that, we're going to go into mesh settings, and under mesh settings I'm going to give it a absolute mesh size of about 0.5 inches, and we'll say generate mesh, and so it will remesh all those parts. keeping in mind that we could use our mesh table to assign different mesh sizes on the different parts if we needed to do that as well. Okay, let's say okay to that. Now at this point I have my material, I have my mesh, I have loads, I have constraints. Let's go ahead and give this analysis a run. Alright, so the analysis is beginning now, and we can see here very quickly I run into an error, and there's a fatal error, E5004. The stiffness matrix is singular or not non-positive definite, and it tells me the solution has failed. The reason for that is because I do have this assembly, right, and I have fixed this component back here, but I don't have any of the other parts fixed. We didn't define any sort of contact. So when I apply the load to the inside circle of the yellow yoke here, what's the relationship of the yellow yoke to the spacer part? I haven't defined any relationship between them, and since this force is off in the x direction, we have no constraints on that yoke or any of the parts that are fixed to the yoke that are stopping the x direction translation, so that model fails to run. So we haven't defined our contact, and that's what we're going to do now. So if we go up to the panel here, we can see there are a couple different ways that we can define solver contact. Contact in general. The first one of those is solver contact. So it says automatically generates contact between elements at the runtime. So I could utilize this one, right? Remember we went in here and we saw that the default contact was set to a bonded type of contact. So if I went ahead and said use solver contact and I run the analysis, then the program's going to determine where it needs to apply that bonded contact, and that would probably work just fine for this analysis. Another option that we have is manual, and manual says that you are going to define where the different contacts happen. So normally, let me hover over that again. You can see the example that it shows is like a sphere dropping onto a cantilever beam. So those parts aren't initially touching, so I could go into my manual contact and before I ever run the analysis, manually specify the bottom surface of that sphere, for instance, and the top surface of the cantilever. And it's nice, you can see in that image that they have split up, for instance, the top surface of that cantilever beam to kind of isolate where the contact is going to happen. And I mentioned that in one of the slides earlier in the presentation that you might want to do that just to kind of isolate the amount of contact that you might have in the analysis. So certainly we could go with manual, but I don't want to have to go through and individually pick out all the mating surfaces here. So generally what I start with is auto, and we'll go ahead and do that. So that automatically detects the contacts and it places them into the menu tree over here, surface contacts, and if I expand that list, then I can go down and you can see it's highlighting on the model as well. There's my different contact pairs. So there's the front face of the yoke and the back side of the spacer, for instance. And let me right click and edit here. And I wanted to right click and edit so that I can show you some of the options in here. So you can see the two surfaces that are involved in this particular contact pair. But there's also a lot of other options here. So from the upper right hand corner, this is where we can set our different types of contact. So we can set it to a separation, to allow sliding or pulling apart, bonded, making it fully fixed, and so on as per the description in your earlier slides. We also have the different penetration type here. So by default, it's at a symmetric type of contact. So what that says is the master entity cannot pass the surface or faces of the slave entity, and likewise the faces of the slave entity cannot pass through the surfaces of the master. And if you wanted to make it faster, you could set that to an unsymmetrical contact, so it's just looking for the one direction type of penetration. But I'm going to go ahead and leave it at symmetrical. A little more what do I want to say, computationally expensive, but also more robust in making sure the surfaces don't pass through one another. The other thing I'm going to talk about here, I'm going to jump down a little bit, is the maximum activation distance. And I'm going to let the program decide. So with it checked and not defining any value there, it's going to utilize a fraction of the model size in order to determine the zone or the distance in which it's going to look for nodes on opposing surfaces and whether we're going to consider them in contact or not. But again, as I mentioned in one of the slides, you can always type a value in here if you have a gap. So if I had a small gap between the yoke and the spacer here, if for some reason there was clearance between them, but I still wanted them to be bonded, if that gap were say 1/1000 of an inch, I might set my maximum activation distance to something like 15 or excuse me 0.0015 or even 0.002 of an inch, something like that, to make sure that those nodes are captured for the contact settings. Okay, so I'm not going to make any changes in here. I'm just going to leave it just the way it is as it was set up by the automatic option. And let's go ahead and run the analysis. And just before I run the analysis, let's take a note here from the meshing that I have 8,933 elements. And we'll go ahead and run it. 8,933 elements, and we'll see that again. We're going to examine this log file a little bit. Okay, so that time, now that I've added in the contact, you can see the Nastran solution is complete. And there are my results. So my max stress is 3,785, and as far as the yoke goes, given the constraints and the loads, the stresses in there are all relatively low. If I come around and I look at my geometry, I can see where my max stress is occurring is between the plate where it gets bolted and the spacer that's there, kind of in the one of the notches of the geometry. So this might be one of those instances that I was talking about in one of the prior slides, that maybe we simplified the geometry too much. We can also see high stresses right here. Would this actually occur in reality? So what we did here is we defined this all as bonded, right? So you can see that I'm getting a high stress here. And why is that? Because I fixed this surface. At the opposite end of the model, I'm pulling on the yoke. So you can see that the yoke is also pulling on this spacer. And so I get a stress here, and I get a rather high stress here, where in reality, wouldn't that probably be in a surface or separation type of contact? Allow some sliding here, and then why can't I do that in this model? The reason I can't do that in this model is if I set separation between this spacer and the yoke here, and I only have it fixed here, well, the yoke's just going to slide right out from underneath the spacer, and it's really the bolt here that's probably keeping this all together. So this is probably an oversimplification what we did here, and I mentioned sometimes you might have to go back and add some additional geometry back into the analysis. And that is, of course, presuming that I need to analyze all of this geometry. If I'm just looking to see what happens in the yoke itself, if that's ultimately the point of my analysis, then I have too many parts in here, right? I could just hold this end of the yoke perhaps and put a load on the other. So there's certainly some things to consider whenever you are whittling down a model from an assembly perspective and trying to decide how to set up this model with what sorts of contact. So before you ever begin an analysis, might be good to consider what the various contacts are going to do to the parts that they are mated with, and whether that is a reasonable approximation of what's actually happening in the real world model. While we're in here, I'm going to take a look at one other thing in the results environment. Let me right click on the von Mises here, and I'm going to say that I want to edit that. So that brings up a results dialog here, and one of the things that we talked about in one of the earlier slides of the PowerPoint was, for instance, that example of the ball dropping onto the cantilever plate. So the ball drops maybe a distance of an inch before it makes contact, right? And we're always going to exaggerate the deformation. So there is where on the Deform Options tab, this is where that exaggeration takes place. And so what I mentioned was, if it looks like that sphere had passed through the cantilever, for instance, it could just be that the displacement on the sphere is much larger than the displacement on the cantilever. So as we exaggerate that 2 times, 3 times, 4 times, the sphere is going to keep looking like it's going a lot further than what the cantilever does. So in those sorts of situations, when there's a gap that gets closed before contact is made, you want to look at the actual displacements in those situations. So you can just click actual, and then the visual of the model, the deformed geometry will change itself to a value of 1, or if you need to, you can type in a value of 1 there to see the true display shape. And then you can see whether the parts are actually passing through one another or not. Okay, let's cancel out of that. The one last thing that I wanted to show here is, we talked about in a number of slides back that when you include contact, even if it's a case of a bonded contact, it adds elements to the model in order to accomplish that contact. So in this case, we can see we have 8,933 elements, and if I go into the Nastran output, we can see that again. I'm at the very bottom of my log file here. Let me go back up. Alright, so let's scroll down from the top of the file here. So right here, we can see we have one subcase. We can see how many grid points or nodes. We can see how many elements we have in the model here, right? So there's 11,208, and a portion of that is a function of the contact segments that get generated. So for all of the individual contact pairs between the various parts, you can see there's extra elements being added in: 163, 169, 549, 510. So these things will add to the simulation time. So just keep that in mind. And then also keep in mind that if it is a surface contact, or if it's a separation, or if it's a sliding contact, those three in particular, over top of the bonded type of contact, are going to iterate, and that iteration is also going to add time to your analysis. So just plan ahead whenever you are setting up the analysis. But again, by no means should you avoid contact. Just put a little bit of thought into your analyses about what sort of contact, how much are you going to simplify the geometry, and what the stability of that model might be, given how you're setting it up with the various types of contact and the components that you do include in the analysis. Okay, thank you.